Hello everyone. Today on behalf of my co-authors, I will present you our work on trigger action programming via conversational approaches. So our work stems from the rapid and continuous growth of the Internet of Things. The IoT is nowadays a well-recognized paradigm that already helps us in several situations. Every day, people interact with a growing number of internet-enabled devices and web applications in many different contexts, ranging from smart homes to smart cities. And the result is a complex network of connected entities, either physical or virtual, that are able to interact and communicate with each other, with humans, and with the environment. In this context, end users can nowadays exploit many different visual programming platforms to directly personalize the joint behavior of their devices and web applications on the basis of their personal needs. And one of the most common tools in this field is probably if this then that. Typically, such platforms adopt a trigger action programming approach. So, for example, users can define trigger action rules like if the surveillance camera recognizes me, then turn on the smart thermostat, or if I publish a post on Facebook, then share it on Twitter. The video exemplifies such a rule definition process in if this then that. So by clicking on the this button, the user starts to define the trigger by browsing a long menu of supported devices and online services. It can select a connected entity to be used for monitoring the trigger. And in this case, the user selects the location provider of her smartphone. Then the user can select a specific event to be monitored by the chosen service, and in this case, the user selects a trigger to monitor the entering in a specific geographical location. And finally, the user completes the trigger with the required details, for example, the specific geographical area. And after defining the trigger, the user clicks on the that button and it repeats the same 3 steps to link an action to the trigger. Despite apparent simplicity, the video highlights one of the main drawbacks of platforms like if this and that. They model smart devices and web applications on the basis of the underlying brand or manufacturer, and as a result, the number of possible connections between different triggers and actions is huge, and it is continuously growing. And this makes the definition of trigger action rules a complex task because users are forced to browse a very large menus with thousands of elements displayed in a meaningless order. Previous works demonstrated that when personalizing their devices and services, users think about abstract personalizations rather than focusing on specific devices and services. They would like to illuminate a room or increasing its temperature independently of the involved connected entities. And recently, popular conversational agents like Amazon Alexa and Google Home have opened the way to interact with connected entities in a more abstract way via natural language. However, while we could exploit them to empower users in defining technological independent trigger action rules, then the problem is how to properly map abstract triggers and actions into executable commands over real devices and services. Stemming from this challenge, we developed ATAP, a conversational and semantic-based recommender system able to map an abstract intention of the user to a set of if-then rules that can be executed over real devices and services in the user context. So to start introducing ATAP, let's start with some background information. In particular, it is important to understand what is a personalization intention. We defined it as a goal-oriented activity that a user would like to be automatically executed in her environment of choice, either physical or virtual, under given conditions. As an example, let's suppose that I want to personalize the temperature of my indoor environments when I'm going to use them. By exploiting platforms like if this and that, I have several possibilities. I can start by setting the temperature on the Nest thermostat in my home at a given hour. And I can do the same for the Netatmo thermostat in my office. Obviously, I can use such an approach for different times of the day, for example, to turn on the office thermostat in the morning while turning it off in the evening. And besides using the time of the day, I can also use other ways to identify the fact that I'm entering or leaving a place. For example, I could use my smartphone position to identify that I'm near home. And furthermore, besides thermostats, I can personalize other temperature-related devices as well, like the bathroom heater in the figure or the air conditioning system in the office. And finally, I can also imagine alternative ways of influencing the temperature of an environment, like opening a window. So given an abstract personalization intention, the goal of ATAP is to first identify the set of trigger action rules that can satisfy it, and second, filter this set to propose the most promising rules only to the user. To reach this goal, the system implements a multi-step procedure. First, the user can interact with ATAP to communicate its abstract personalization intention via natural language. To this end, we exploited a semantic-based conversational agent that uses the Dialogflow platform and the Eupont ontology. The Eupont ontology in particular is a model that abstracts details such as brands and manufacturers by categorizing the if this and that triggers and actions under a hierarchy of classes that model the provided functionality. Furthermore, the ontology models all the supported connected entities on the basis of their final capabilities, and she can store contextual information such as the position of the entities in the user context. Thanks to a common vocabulary defined in Dialogflow, ATAP is able to map the user input to Eupont classes. In the figure, for example, the word notification is linked to the information action class, while the word decreases is linked to the decreased air quality class. Such a mapping allows the system to get a first set of candidate trigger action rules. These candidates are then combined with the long-term preferences of the user, like the rules that the user has already defined in the past, as well as the devices and services owned by the same user. And such a process ranks trigger action rules according to a semantic association metric that is computed by weighting triggers and actions through a Jacquard similarity index. And the output is a first set of recommended trigger action rules. If the user is not satisfied with the recommendations, it can iteratively collaborate with the system to improve the recommendations. At each refinement cycle in particular, the user can provide ATAP with a short-term preference by selecting the recommended rule that is more in line with its intention. This feedback is used to reweight trigger action rules and propose a refined set of recommendations. And to this end, the system can use three different reweighting policies. The promote policy promotes rules that are similar to the selected feedback. The penalize policy penalizes the rules that haven't been selected. And the promote and penalize policy is instead a mix of the previous ones. We evaluated the recommendation process adopted by ATAP through different offline experiments with simulated users and real-world data. We used a public dataset of trigger action rules extracted from if this and that to simulate the interaction between users and the system. We explored two different research questions in particular. First, we assessed the recommendation process of ATAP by varying its parameters and reweighting policies. And second, we compared ATAP with state-of-the-art recommendation systems. You can obviously find more details on the paper regarding the conducted experiments, but to summarize, as shown in the table, the first part of the evaluation allowed us to find the best configuration for the ATAP algorithm. In particular, the promote and penalize policy performed better in terms of hit rate and similarity with the target item. And in general, ATAP performed better when considering both the current intention of the user and its long-term preferences with the same weight. For what concerns the second research question, we found that ATAP outperformed other similar recommender systems like RecRules and N/P in terms of precision and recall. And as you can see in the right part of the table, precision and recall improved after 10 refinement cycles. Furthermore, we also compared the hit rate and the similarity with the target item between ATAP and N/P, that is the other algorithm that supports refinement cycles. And the two charts confirm that ATAP is in general more effective in recommending rules able to satisfy the user intention and preferences with respect to the other evaluated algorithms. To conclude, we are aware that one of the limitations of our work is that we evaluated our system with a single dataset. Unfortunately, differently from other domains like movies and songs, recommendations in the trigger action programming context are in their early stages, and to the best of our knowledge, there are no other public datasets of trigger action rules. So in future works, we aim at evaluating ATAP with real users, possibly through in-the-wild experiments. Furthermore, we will also explore the adoption of different trigger action programming paradigms by supporting, for instance, trigger conditions and multiple actions in the recommended rules. And this concludes my presentation. Thank you for your attention, and I'm open to questions.